Good morning, everyone. I'm delighted to take an opportunity to introduce our chief guest of the day, Dr. Joshi Garu. Dr. Joshi is an associate professor of mechanical engineering at the Indian Institute of Technology, Guwahati, India. His research interests include micro
చెప్పండి.
Good morning, Honorable. Dr. Joshi is an associate professor of mechanical engineering at the Indian Institute of Technology, Guwahati, India. His research interests include micro, nano, and precision manufacturing process with a focus on applications of gases in manufacturing, thin-wall machining, single-point diamond turning, CAD and CAM, and manufacturing automation. His research addresses both the basic as well as applied problems pertaining to this manufacturing process. Dr. Joshi Research Group also works on the development of intelligent machine tools and CAD systems. They have developed a massive open online course on automation in manufacturing and a web course on electronics and manufacturing automation. As a part of the Government of India's flagship project, National Program on Technology Enhancing Learning and People. His areas of specialization in manufacturing engineering and the abroad area of research is advanced manufacturing technologies. We all are thanking you, sir, for considering our request for the keynote session helping your busy schedule. We are happy and looking forward to learning from this session. Very good, sir. Thank you. I invite Joshi sir to continue. Sir, please continue.
Yeah, thank you. Am I audible?
Yes, sir.
Yes, sir, it is audible.
Fine. I cannot share my slides. You give the permission to share the slides. The owner of the group or owner of the meeting, please provide the permission to share the slide.
Yes, sir, permitted, sir.
Yeah. My screen is visible to you all. Whether my screen is visible?
Yes, sir. Yes, sir. Yes, sir. Yes, sir, it is visible and clear. Yes, sir, you can continue, sir. Sir, please continue.
Yeah, I will continue for better. I will switch off my video. Talk about this. Fine. Yeah. Good morning, everybody. And will you please switch off the? All right, you mute the mic, right? Thank you. Good morning, everybody. Myself, Shri Krishna Joshi, and I congratulate Bapatla Engineering College for taking the initiative and conducting a wonderful 2 days event on mechanical engineering and emerging technologies. I initially thank to the administration of the Bapatla College for inviting me to share some of the technical results or the experience on one of the topic that we gained here at IIT Guwahati. Well, as you all know that the topic given or topic rather I selected here is manufacturing technologies, and that too which are coming up or which are getting advanced manufacturing technologies. Well, in advancements nowadays, lasers are being used often. Lasers are being used very widely in manufacturing industry. Lasers are basically, as you know, the monochromatic, you can say, the core and beam of the photons. And then by using the lasers, we are heating up the material, and by that thermal energy, we are getting the things done during our manufacturing operations. So one of the very interesting application, that is forming, that I would be discussing today with you. We will be having little fundamentals of the laser-based forming, and then what could be the research possibilities in laser-based forming. That I would like to talk to you in today's this lecture. Okay. Before to start with, I must, acknowledge the efforts put by my first PhD student, Dr. Ravikant, who worked on this topic, laser-based forming, and many MTech and BTech students who contributed to this particular area. In addition to this, I acknowledge the guidance or mentorship of Professor U.S. Dikshit, and the cooperation by other my colleagues, Dr. Sachin Gautam, Professor Pankaj Bishwas of IIT Guwahati. Well, I'm leading a group of very enthusiastic researchers, students, as well as faculty members, that is Advanced Manufacturing Research Group at IIT Guwahati. We basically apply laser for forming operation. We also work in the area of ultra precision machining, that is single point diamond turning operations, which are used to manufacture optical components, mirrors, and you can say the molds which are required for contact lenses and various precision parts of the defense and the aerospace applications. Moreover, we also work in the area of precision manufacturing, particularly manufacturing of thin walls, ultra thin walls up to the range of 0.7 mm, that is the 700 microns. And laser also we are using for machining operation. It's not just deformation or plastic deformation. We are using laser for material removal as well. Direct laser application also we do, and laser induced plasma micromachining. So by using lasers, plasma is getting formed, and that plasma will be utilized for the ablation of transparent materials. Particularly lasers, we are using here the transparent materials processing, because lasers are basically not well known for transparent materials, because they will just pass through it. There will not be any absorptivity of the laser beam. So how to tackle this problem? There are various techniques that are being developed on the laser-induced plasma micromachining. Well, but today I would be talking only on the laser forming process. And you can just visit my profile at Google Scholar or my profile at IIT Guwahati, and you can find my publications, which will give you the idea about all these techniques and technologies that we develop on variety of these processes. Fine. So outline of today's talk, like first we'll talk about what do you mean by laser forming, what are the various mechanisms of forming, what are the various parameters or performance measures which are being used to study or to apply or to employ the lasers in forming operation. What are its advantages? Some limitations are also there, that also we will discuss, and then applications of the lasers in forming operation. Further, the research that we are carrying out at IIT Guwahati on forming of difficult to form materials, variants, and the advancements, and that's summary also we'll talking about. Well, so let us move ahead and look at these two parts, that is the fundamentals and the R&D activities. So first, let us talk about the fundamentals. Metal forming or material forming, it's a very important manufacturing process. Overall, the manufacturing processes we can classify to primary processes and secondary processes. So material forming is coming into primary manufacturing process after casting. Many of the components or even casting and forming are being considered as the primary manufacturing processes. So we can do forming either by applying the compressive stresses such as the rolling and extrusion. These are the two examples of this. Or we apply the tensile stresses, the wire drawing, manufacturing of wires. So when we apply the tension, then we can produce wires, and when we apply compression, we produce roll sheets or the extruded components. In some of the applications, we apply both the stresses, combination of stresses that we call bending or the sheet metal forming. The problem with the metal forming is that it requires a lot of mechanical tools, like punch and dies are required. And to manufacture them, we need to put a lot of efforts. We have to design them, we have to manufacture them. So that consumes a lot of time. So lead time or the product lead time is very high when we go for the mechanical based material forming. Moreover, these components or these processes are bulky, or the equipment are bulky. The process is noisy, with a lot of noise or interference may be there, and it's tedious. It's not that good for the human operator or the workers or engineers, those who are working in the industry. So here one good solution to this problem, can we use some non-contact type of process to deform the components or the parts? And can we use some sort of thermal energy beam? We can have a beam which is made up of which is having a thermal energy, and that can be created by any of the source. It can be a laser-based source, it can be ion-based source, or it can be some heat energy plasma-based source. So laser can be utilized because of its very peculiar nature. It's very good advantage that we can focus it on a very small dimension. So high energy consumption and spring back also are creating problems to the material forming. Now in laser forming, it's a very interesting technology. Here we are having a plate or a sheet, and then we are applying the laser over the plate or sheet. This, of course, this has to be a conducted plate, okay, conductive. So when the laser is getting applied, which is not in contact, the head is not in contact, there is some standoff distance between laser head and the work part. Then what we are getting thermal stresses on the surface. And these thermal stresses which are induced due to controlled heating. So we have to apply the laser beam energy in such a way that it will not burn the component. It will not melt the surface. It will not melt the material. So it will just heat up the material in a controlled fashion. So when we achieve this, we can generate thermal stresses. And due to thermal stresses, we are generating thermal strains. And that strains are utilized to deform the work part. So how it is possible? Let us see. Well, where can be used? These laser-based forming technology can be used in sheets, plates, foils, and pipes also can be bent. And it is even suitable for metals and non-metals, and even composite materials as well. The advantage, as I mentioned, no need of the dies or the tools. Press is not required. You can simply have a laser with sufficient laser power and then you can utilize it for operation. So laser, as you know, it's widely being used for a variety of other applications, such as uh, ablation, melting and vaporization, drilling, fine cutting. Then laser is widely used in the industry, particularly the automobile industry, for welding operation. Engraving we do. We can write letters. We can write on the metal parts by using lasers. And the peculiarities that are, it's a contactless machining operation can also be done. But how exactly the lasers are used for the deformation? So how exactly it is being done? So for that, there are various mechanisms are there. The first mechanism is the TGM, that we call temperature gradient mechanism. So in temperature gradient mechanism, we are taking the sheet and consider this is a sheet, and here this is the cross section of the sheet. This is the top surface, and this bottom surface, we are applying laser energy on the top surface. Now consider the thickness of this or the laser beam diameter is equal to or less than the thickness of this particular sheet or the plate. Now what is happening now when we are heating up on the top surface, the temperature of the top surface would be very high, and the heat energy will be conducted across the thickness, across the work volume of the workpiece. Now this heat conduction is dependent upon the conductivity of this particular plate. Now what is happening if the heat conductivity is less, then there would be more heating at the top surface and the heat dissipation naturally is less. So since the more heating on the top surface and less heating at the bottom surface, so we are getting some sort of gradient that we call temperature gradient. So there is more temperature at top and less temperature at the bottom. So we get a gradient, and we require to have a steep gradient. Why steep gradient is required? So when we apply the thermal energy here, these fibers, the top surface fibers are getting expanded. They're expanding themselves due to the thermal energy. But the problem is that the surrounding medium, so this medium is at the normal temperature. It is at the ambient temperature. And here we are applying, say, 500 watt. So the temperature may be, say, around 500 degrees Celsius. But immediately or adjacent to this laser beam energy, the temperature may be at 40 degrees Celsius. Along this direction, it may be around 20 to 25 degrees Celsius. Now, this huge difference between the temperature at the irradiation location and the adjacent phase, that is creating the compressive stresses. Why compressive stresses? Because these fibers are trying to expand themselves, but the cooling region is restricting the expansion. It's not allowing the fibers to expand. So when it is not allowed to expand, it is creating compressive stresses on the top surface here. So these compressive stresses are leading for the deformation. So when laser beam energy is being applied, so here you can see the top fibers are trying to expand at start, but the surrounding region is at the cooler phase, they will not try to expand. So when the laser beam is moved over that area, it has passed. There is no laser beam now. So as the laser beam has moved, the compressive stresses, they are dominating over these tensile stresses here. The compressive stresses which are along this direction, they are dominating. They are at a high strength, much larger magnitude than the tensile stresses. And due to that, we are getting bending of the work part towards the laser. So we are getting the bending of the work part towards the laser, and that is called as the temperature gradient based mechanism. So by just having controlled heating, we are deforming the work part material. So this is not that well known. We are doing it quite since long time in hull manufacturing, ship building as well. There is a concept called flame bending. So we are using flames for bending of the hulls of the ships. We are just heating up the material, and then we are applying some mechanical load to deform the work part. But here we are not applying any mechanical load. We are just heating it up, and we can do the forming. So one video is there with me. I would like to just show that video to you so that you will understand it in a whether my video is okay. Can you see it?
Yes, sir.
Yeah, right. Okay.
Yes, sir.
Now here you can see this is a laser head basically, and this video we have recorded on 2.5 kilowatt CO2 laser machine at IIT Guwahati. And this work material is mild steel basically. So we got at initial level on mild steel we did the experiments. So here you can see this is the sheet. This shows the thickness. This is the thickness of the mild steel sheet, and this is the laser beam head. So when the laser beam is applied over the surface, you just try to see the deformation basically. So here you can see. Yeah, one pass is over. The sheet was horizontal. Now a very minor deformation occurred. So about 1 degree deformation. Sometimes by naked eyes, it may not be even noticeable as well. So then to have the much larger deformations, we have to go for multiple irradiations. So one more irradiation you can see. Now you can clearly note that there is a deformation occurred. It was perfectly horizontal, the mild steel earlier. Now with the heat energy, it was deformed here. So here you can even notice around 2 to 3 degrees of the deformation occurred for multiple number of passes. And that is the beauty of this particular methodology to go for laser non-contact based the deformation. And let me go back to our slides. Now this deformation that we got, it's for some sort of process parameters that you can notice here. So these are for the 400 watt, the speed of the scanning. Laser was moving over the scan sheet. It was around 400 mm per minute. And the beam diameter was about 7 mm, and total number of irradiation that we did for the three number of passes. Now, what is happening? We did the numerical analysis as well. How exactly this can be understood? So if you look at the temperature on the part, let us consider that the laser is moving from one end to other end. A is the point; it's at the top surface, and B is at the bottom surface. So if we plot the temperature at point A and point B with respect to the time, the laser application time. So what temperature graph we get? So this is the temperature graph. As the laser beam is moving over, so we are getting a peak, when the laser beam comes at a point A. So at point A, we are getting a temperature about 450 degrees Celsius. And at the same time, the temperature at point B is around 250 degrees Celsius. It's around 250 degrees Celsius. So there is a difference of around 200 degrees Celsius between point A to point B, and this difference is creating the stresses. This difference is generating the stresses at point A and B. So this temperature stresses that you can consider here, these are the compressive stresses which are being generated at point A and point B. So these stresses are generating the strains, and you can just notice the strains. This is the strain. Again, it is the compressive strain that we are getting here. So that's why the magnitude has been shown in negative. So compressive stresses, and the difference between compressive stresses as point A and point B is giving us the bend angle. So here for a single pass, we could achieve a bend angle of only 1 degree. It's not that much. So then you will say that, sir, what is the utilization of this kind of bending? So my friends, it's very easy to bend for 10 degrees or 15 degrees or 20 degrees, but it's very difficult to have a precision bending of 1.5 degrees or 2 degrees. So these kind of deformations are very much essential in, you can say, micro electromechanical systems, MEMS basically. So if you just try to open up your USB drive or a pen drive, you will find that there are connectors, and these connectors are deformed. So these connectors are deliberately bent. They are not horizontal. So why the bending has been given? So that there would be efficient contact of the USB with the system, whatever it may be, laptop or a desktop or anything else. So to have the proper contact, the connectors are little bent, and that bent is not 1 or 2 degrees or 3 degrees. So how these bends are being manufactured? These are manufactured by using such a precision manufacturing operation. So Philips started using lasers for deformation of the connectors of their CD drives. And now we don't utilize the CD drives anymore. Even DVD drives also we don't utilize. We are working on the USBs, or nowadays Wi-Fi data transfer we are doing. But that time for the efficient contact, we can have 1 or 2 degrees of this sort of deformation. But if you go for the multiple number of passes, you can certainly have the major deformation of the work parts. Now, what will happen if the laser beam is getting expanded? If suppose you are having a very wide laser beam, so how to tackle this situation? What will happen? So consider we are having only 2 mm of thin sheet, and the laser beam diameter is about 8 mm, 4 times more than that. Then simply more energy will be being applied, and we may not able to get the temperature gradient here. So there will not be any temperature gradient. The temperature along the thickness would be same. It's not getting reduced. So whatever the temperature at the top and the bottom surface would be same, and due to that, we may have some sort of uncontrolled deformation. Suppose you are getting a very thin foil of a metal, and then you can just keep it on or just hold it on candle. What will happen? It will deform in an uncontrolled fashion. In a similar way, if we are having a thin foils or thin sheets, and if the laser beam diameter is more, then we can produce the buckling mechanism, but it is in an uncontrolled fashion basically. So here you can see the bend angle would be more, but here you can notice you can have around 10, 15, 20 degrees of bend angle during this buckling operation. But what will happen if the laser beam is having a very low in magnitude? The diameter of the laser beam is low in the magnitude comparison to the thickness of the sheet. So what will happen? So in this case, we are getting some sort of deformation, but that is not noticeable to us. We will not be, notice it in a proper way. So simply laser will come and will irradiate. So what will happen here? So the laser beam energy will be transferred into thermal energy, and thermal energy is being dissipated or conducted inside the work part. So there is a expansion and then contraction, expansion and contraction. So due to the expansion and contraction, there is a formation of bead. There is a formation of some thickening at the top surface. But this thickening is nothing but the volume which we are getting from its lateral portion, lateral volume basically. So here we are doing a number of irradiations, say around hundreds, 200s, 300s. Then what will happen? There is a bead formation. Bead means there is a, you can say, a protrusion will occur, or there is a swelling will occur. And this swelling is nothing but a volume. So this volume will be from the lateral region. And as there is a volume transfer or mass transfer from the lateral region, the width is getting changed. The width is getting altered, and width is getting reduced basically for 1 or 2 mm. And that is called as the upsetting mechanism. So we are just modulating, we are just altering the width, and that the width changes can be seen over here. So this is called as the upsetting mechanism. So this is the initial shape, and this is the final shape, which can be seen over here. So this is the temperature, which is almost same at the top and bottom surface, but the stress again would be almost same, and the plastic strength. So only just thickening will occur, and that will be leading to this sort of the deformation. Fine. So what is the application of this particular process? So the application of this process is that, suppose you want to attach, or when we want to you can say weld 2 different sheets, okay, and during the welding of 2 thick sheets, metal sheets, at the assembly, for example, on the ship building, the ship buildings, we are designing the ship into patches, and then the patches are to be assembled on site. They are to be welded on site. At the time of assembly, or at the time of welding, we came to know that there is some sort of overlap. There is an error of 1 mm or 2 mm. But when we apply the cutter over there, now to have the welding gap, to generate the welding gap, we have to apply the cutter. But cutter size is 5 mm or 10 mm. The cutter thickness is 5 mm or 10 mm. Then the gap would be too wide. So we want to have only 1 mm gap. So to adjust or to repair or to maintain such sites, to have just little deformation of 1 or 2 mm, we can use the upsetting mechanism. Now, if you try to compare these forming mechanisms, you can find, I have just summarized it here, the TGM, buckling, and the upsetting mechanism. For TGM, we required high feed rate. For buckling, low feed rate, and here also low feed rate. And here you can see that buckling is generating very high bending angle, but upsetting and TGMs are generating very low buckling. There are various process parameters which are affecting, like laser power, feed rate, the beam spot diameter, and number of scans, which are the energy parameters that we call, which are controlling the laser beam energy. Whereas the absorptivity, thermal properties, and mechanical properties, these are coming under the material properties domain, which are also affecting the laser process. So how the beam energy, so if suppose the power is, you are applying or you are increasing the power. So at low power, what we notice that there is no sufficient energy to deform the material. So at around 100 watts or lesser than that, we did not find any deformation. So we increased the power. We found that at around 300, around 250 to around 600 watt, we got very good results about the deformation. But if you increase the power beyond that, around 700 or 800 watt, again, there was no deformation. And the reason is very simple, that so this extra energy or the large energy that we are applying, that is getting utilized for the phase transformation. The solid was getting transformed to the liquid. There was a melting was occurring. And when we know that when there is a phase transformation, most of the energy is getting consumed for the phase transformation. So there was no plastic deformation at the higher laser powers. So it is a very good optimization problem, as the laser power is having the non-linear behavior with the bend angle in this case. At low power cut, there is reversible elastic effects as well. So because not much plastic deformation, so the elastic or reversible elastic effects of the threshold energy itself is creating or itself it's getting back the work part to the normal position. Well, velocity is also very interesting parameter. As we increase we should have a sufficient velocity of scanning. If the velocity is low, then there would be more heat transfer at one particular location. So we may not get the TGM, we may not get proper temperature gradient from top to bottom. So if you increase to around 200 mm per minute, then we may get a very good bend angle. But if further increase up to 4,000, 5,000 and beyond that, then what we notice that there is no sufficient time for the interaction of laser beam with the work part. So there is no time actual for the heat transfer from the laser beam energy to the work part. So that's why the bend angle was less, the plastic deformation was less. Diameter was having mostly the linear behavior. So as we increase the beam diameter, keeping the power constant, so as you know that it certainly reduce the flux, the density of the heat application, and due to that, as the reduction in the flux, the deformation would be low. And energy absorption is another very important parameter which is affecting lasers. So energy has to be properly absorbed, but some of the materials like aluminum or the stainless steel, we face the problem, and it's very natural. If a lot of energy is getting reflected, then there will not be good deformation will there. So what is the solution to that? So here many of our colleagues have tried, or many students, MTech students like you, have tried many things. They applied cement, they applied soda lime, or they even applied the graphite coating to improve the absorptivity. And we found that by applying even a black paint, if you just apply a simple black paint as well, you can enhance the absorptivity. So this reflectivity issue has to be taken care in a very serious manner. Otherwise, by reflection of the laser beam, the mirrors will get damaged. The laser beam mirrors, those who are used to divert the laser beam energy on the work part, will get damaged. So we have to be very careful about the energy absorption here. And number of scans, as we increase the number of scans, we have seen that the cumulative angle is getting increased. So the total bend angle, what we can see here, is getting increased with the number of scans here. But the bend angle per scan is getting reduced. So that you can notice here, the bend angle per scan is getting reduced, but the cumulative bend angle is getting increased. So the reason is that the bend angle per scan is getting reduced is due to strain hardening. So as you keep on applying the laser beam energy, there is expansion and contraction, and the material property is getting changed. And for the next laser scan, we are losing the material properties. The material properties are getting deteriorated, and due to that, we were not able to get the proper bend angle for the subsequent laser passes. Material properties, here conductivity of course is very crucial, it's very critical parameter, and then coefficient of thermal expansion. So as we notice that if the thermal conductivity is less, then we can achieve very good temperature gradient, otherwise it's very difficult for us. Moreover, there is another parameter, that is the strength of the material. If the strength of the material is less, for example, uh, the the you can say the yield strength basically. So if the yield strength is less, then certainly we may not able to get proper uh, deformation. And if the high strength is there, then also it is the problem. So the strength of the material is is to be according to the requirement here. Plate geometry, the thickness, as we have seen that the thickness is the most critical parameter. By applying uh, the laser beam energy, which is in proportion with the thickness. If if the work part is thicker, then it will go for offsetting mechanism. If it is very thin, it will go for the buckling mechanism. So when we are applying the energy, the thickness has to be considered during the operations. Then what are the various advantages? These advantages are just listed over here. So the lasers are reducing the productivity. The lasers are increasing the productivity because the lead time is getting reduced. They're reducing the lead time. And as there are no external or you can say the tool, mechanical tool being involved, the lasers are considered as cost effective. So now you will say that, sir, how the lasers are being cost effective? Lasers are very expensive. So almost all the companies or all the small scale industries nowadays, they do have lasers. The laser is no more that costly, expensive technology nowadays. Even small lasers can be procured. People are using lasers for even small operations at their tool rooms. So it is a very cost effective, and it's very good for small batches. So if we are manufacturing mechanical tooling, it has to be there for a long, or you can say for long time for mass production. But as most of the productions in the companies are at the batch, so the lasers can be employed without much spending and without much spending the time and the cost as well. We can generate accurate deformations or patterns. So we can have various complex shapes can be manufactured by using lasers, and laser can reach the unreachable areas. So many a times that mechanical tools are having the problem that at certain point we have to deform. So there it's not possible to have mechanical tool that to reach and then you apply the energy on that. So lasers can reach at some unreachable areas, and the accessibility is the advantage over here. So we can deform any material like brittle, hard, or heavy materials such as titanium alloys, nickel alloys, ceramics. We can go for various shapes such as dish shape or a screw shape or a cone shape or a saddle shape by using the laser beam energy. We can even work at a micro scale by using the lasers. As I mentioned, we can easily have 1 degree or 1.5 degree or 2 degree precise bending that can be considered as a micro bending. Micro bending literally doesn't mean you have to go for 0.001 degree or 1.1 degree. It's not possible even to locate. Here, the micro bending is considered as, in comparison with the macro bending, we can have a very small bend angle that can be considered as the micro scale bending. And with CNC technology nowadays, as you know that, so a lot of CNC technologies we are using for a variety of applications. So we can easily control the process parameters and we can use in the automation process. But what are the limitations to these processes? So capital investment to certain extent is high. If suppose we are trying to employ the laser for heavy applications or for large work pieces, then we have to increase the wattage here. You have to go for the 3 kilowatt or 5 kilowatt, or you can say the 10 kilowatt. So certainly in that sense, the capital investment would be high, but for small applications, it is affordable. So it is a slow process comparatively to the mechanical process, naturally, because in mechanical process, once the tool is ready, then you can just simply do the punching at a very rapid way. In that sense, the laser is that way a slow process. More energy consumption. People are saying that the lasers are not efficient. We have to employ a lot of electricity for that. But that is not true. Here we are deforming the work material. We are not heating up the work material. So in that sense, we are not losing any energy. We are using a very small amount of energy, photon energy, for the deformation. Material surfaces with more reflectivity are difficult to process, but there are solutions as we have already discussed. Okay. Various applications of lasers in the product life cycle can be seen here. For the production